Welcome to the podcast of machine learning. Today, we're jumping straight into, well, one of the really exciting but also kind of frustrating areas in AI right now, vision-based reinforcement learning, VRL for short.
Yeah, VRL. It's basically this huge challenge.
Hmm.
How do you teach something like a self-driving car or maybe a complex robot arm in a factory how to operate just by looking? I mean, its only input is this stream of visual data, basically raw pixels.
Right.
And the goal is to get it to connect what it sees with the best possible action to take next.
And the applications are massive, right?
Yeah.
We're focusing a lot today on autonomous driving, especially using the carless simulator, which is super demanding.
Mm-hmm.
But this tech applies everywhere, robotics, even complex video games. Sounds amazing. But there are these two big roadblocks holding VRL back.
That's really the core issue we're digging into. First, you've got sample efficiency. Or maybe inefficiency is the better word.
Meaning it just takes way too long to learn.
Exactly. The agent learns purely by trying things out itself, exploring its world.
Hmm.
If you only learn from your own mistakes and you have to make a lot of them, well, it's incredibly slow.
Okay, that's one. What's the second?
The second is maybe trickier. It's this idea of a semantic gap. The way the agent represents what it sees, it lacks common sense, basically, task-relevant common sense.
Well, it sees pixels, but it doesn't inherently know, oh, that blob over there is a pedestrian, and pedestrians sometimes, step into the road.
Precisely. The visual encoder, the part processing the image, just doesn't have that background knowledge to make smart, generalizable decisions.
Okay, so that sets the stage. Our mission for this deep dive, then, is to really unpack this new approach called DGC. That stands for Distilling Guidance from Visual Language Models into a Compact VRL Agent.
Yeah, DGC. And it's not just a small tweak. It's aiming for a really different strategy.
How so?
DGC sort of recognizes that VRL agents need two things. Common sense for seeing, but pure RL optimization for acting. And the big idea is to completely separate those jobs. Use the big language models for the common sense, but not for making the moment-to-moment driving decisions.
Interesting. Okay, so before we get deep into DGC, let's look at what people were trying before. What's the sort of traditional VRL approach?
Well, traditionally, researchers tried to improve representations using something called self-supervised auxiliary tasks, or SSL.
Right, SSL. I've heard of methods like DeepMDP or CURL. They use SSL alongside the main RL learning signal, right? Which is often temporal difference or TD loss.
Exactly. TD loss is how the agent learns from reward prediction errors, figuring out if its actions are leading to good outcomes. SSL adds extra tasks, like trying to predict the next frame or the reward, hoping this forces the agent to learn better visual features along the way.
But, as the source material points out, this kind of low-level self-supervision, it cannot provide additional semantic information. It doesn't give the agent real-world common sense.
No, it doesn't. It helps a bit with feature learning, but you're still kind of stuck. The agent doesn't understand physics or traffic rules or what objects mean. It just sees patterns and pixels from its own limited experience.
So it struggles to generalize. What it learns in one specific scene might not apply well somewhere else.
That's a huge problem. It lacks that broad knowledge base that these huge visual language models, VLMs, have. Models trained on basically the entire internet's worth of images and text.
Okay, so if VLMs have all this knowledge, why didn't people just plug them in earlier? I know there have been attempts to integrate VLMs.
There have. But they haven't really panned out for complex real-time tasks like driving. Those attempts usually fall into two main camps.
What are they?
First, you have approaches where the VLM acts as a direct executor or teacher. It directly tells the agent what to do based on the scene.
Like asking the VLM, should I turn left now?
Sort of, yeah. But experiments show this actually performs poorly. The VLM might give infeasible or irrational decisions in specific fast-moving situations. They're good at general knowledge, but not at, say, reacting instantly to a car cutting you off.
Right, you wouldn't want a VLM trying to parallel park based on abstract rules.
Definitely not.
Mm.
The second approach is using fine-tuning, either policy fine-tuning, PFT, or representation fine-tuning, RFT.
So using the VLM's knowledge to give the VRL agent a head start, like pre-training it.
Exactly. Using VLM outputs or internal features as a starting point. And this actually works okay for simpler tasks. Things like maybe AI or some robotics task in MetaWorld where the controls are simpler or the visual input is maybe less cluttered.
But not for something like Carla.
No. When you hit the complexity of the Carla benchmark, continuous steering and acceleration, unpredictable traffic, strict rules, these fine-tuning methods show suboptimal performance. They just can't handle that level of dynamic complexity.
Okay, so it sounds like using VLMs directly for control or just for initialization hits a wall with really hard problems.
It does, and this is where DGC gets really clever. It takes that failure as a starting point.
How so?
The core idea, the real insight is, don't try to push the VLM's knowledge into the policy decoder, the part deciding what action to take.
Okay.
Instead, distill that rich VLM knowledge only into the compact visual encoder, the part that's just responsible for perception, for understanding the scene.
Ah, so you decouple perception from action control.
Precisely, that's the key word, decoupling. This way, you leverage the VLM for what it's really good at, high-level visual understanding, common sense reasoning about the world.
But the actual driving, the moment-to-moment actions, that stays purely in the VRL domain, optimized using standard RL algorithms like SAC.
Exactly. Soft actor critic, SAC. It's a state-of-the-art RL algorithm that's good at continuous control and balancing exploration with exploiting what it knows. So the VRL agent learns the skill of driving through trial and error, guided by rewards.
But its perception is now infused with common sense from the VLM.
Right. And this also helps with the efficiency problem we talked
Right.
about.
How does it help there?
Because the really big, computationally expensive VLMs models like QuenVL Chat or the CLIP series, they are only used during the training phase.
Ah, so they generate the guidance signals to train the little VRL agent's visual encoder. But once the agent is trained and deployed, say in a real car,
The VLMs are gone. You're left with a compact, efficient VRL agent that now has much better visual understanding baked in.
that's a really smart architecture.
Yeah.
VLM smarts during training, VRL efficiency during runtime.
Okay, but here's the crucial bit for me. How do you actually translate that abstract VLM knowledge, that common sense, into something the VRL agent's visual encoder can use? Like you said, it only sees pixels.
That's the magic trick, right? They developed this novel prompting reasoning pipeline. This is the mechanism that converts the VLM's high-level understanding into concrete guidance for the visual encoder.
Okay, bring that down. A pipeline involving prompts. Yeah. So during training, you take the agent's recent history, like the last few camera images and the actions it took, and you feed this into a powerful reasoning VLM, maybe something like GPT-4o or QuenVL Chat. But you don't just ask it a simple question. You give it a very structured set of prompts.
Like instructions for the VLM.
Exactly. It uses a kind of chain of thought prompting structure. First, there's a task definition prompt. It tells the VLM, okay, you are an autopilot expert. Here's the input format. Here's what I expect as output.
That's the stage.
Then a common sense prompt. This injects general safety rules, always avoid collisions, follow traffic laws, that kind of thing. Basic driving principles.
Got it. And the core part.
The core is the chain of thought prompt. This guides the VLM step by step. First, describe the current driving environment. Second, anticipate what might happen next based on that. Third, set priorities, what's most important right now. And only then, fourth, identify the key areas of interest that the agent should be focusing on.
So it forces the VLM to reason systematically before outputting an answer.
Yes. And the output isn't a direct action command. It's a clear semantic category, like a text label. Bicyclist ahead in lane, or a car merging from radio.
Okay, now we have common sense described in text. We still need to get that into the visual encoder, into the pixels.
Right. This is the next step, representation distillation. They use another type of model, a linguistic image referring model. Think SLIP or CRISLI-S. These models are good at connecting text descriptions to image regions.
So they take the text label, like bicyclist ahead.
Exactly. And they use the referring model to generate two things from that text targeted at the input image. First, a pixel-level saliency feature map. You can imagine this like a heat map overlaid on the image, highlighting the specific pixels that correspond to the bicyclist ahead. It tells the VRL agent where to look.
Like a spotlight.
Kinda, yeah. And second, it generates a semantic-related convolutional kernel. This is like a specialized filter tuned by the text description that the VRL agent can use to process that specific highlighted region more effectively. It helps the agent understand what it's looking at in that spot.
Wow. So the VLM, through this pipeline, is literally teaching the VRL agent's visual system, where to focus, and what kinds of features to look for in those areas based on common sense.
That's the essence of it. And to make sure this distilled knowledge is actually useful for the driving task, they add a refinement step.
Which is?
They also include two of those standard SSL auxiliary tasks we mentioned earlier, transition prediction and reward prediction. This helps ensure the VLM's guidance doesn't distract the agent from its main goal of driving well and maximizing rewards. It keeps the common sense grounded in the task.
Okay, the mechanism makes sense, it's clever. But does it actually work? Let's talk results. The testing ground was Carla, right?
Yes, the Carla benchmark. And it's seriously challenging. They use three specific scenarios to really push the agents.
What are they?
First, jaywalk, hashtag JW. Pretty self-explanatory pedestrians crossing randomly, unpredictable behavior.
Stressful.
Second, high beam, hashtag HB. This one involves cyclists, but also adds tricky lighting conditions like glare or sudden changes, which can really mess with visual perception. And third, probably the toughest, highway, hashtag HW. Here, the agent is driving on a highway surrounded by, I think, 20 other vehicles, all moving at different speeds. Merging, lane changes, maintaining safe distances, it's complex.
Yeah, that sounds like a nightmare scenario for an AI driver. So how did DGC do?
It performed remarkably well, significantly better than the baselines. Let's look at the highway scenario, hashtag HW figures. The baseline SAC agent, just pure VRL, got an episode return, which measures overall driving performance and safety, of about 142.
Not great.
No. Even the methods using VLM features for fine-tuning, the PFT approach, they only reached around 264.
Better, but still.
But DGC, with its decoupled common sense perception, it achieved an episode return of 287 plus or minus 47. That's a really substantial improvement, showing much more robust and safe driving in that chaotic environment. It was consistently the top performer across scenarios in both episode return and total driving distance achieved safely.
That's impressive. What about the sample efficiency? Did it learn faster?
Massively so. The paper highlights that DGC showed the best sample efficiency during training. If you look at the learning curves, DGC's performance shoots up much more quickly than the other methods.
Meaning it reaches good driving capability with much less trial and error, fewer miles driven in the simulator.
Exactly, because its visual encoder isn't starting from zero. It already has these robust common sense representations distilled from the VLM. It learns the skill of driving much faster because it already understands the world better.
And is there visual evidence of this improved understanding? Did they look inside the agent's head?
They did. They analyzed the saliency maps, basically, where the agent's visual encoder was focusing its attention while driving.
And
The areas it focused on, the salient regions, were closely aligned with the semantic categories identified by the VLM pipeline. If the VLM flagged a pedestrian, the agent's visual system was indeed focusing strongly on that pedestrian. It learned to look at the right things.
that's cool. It shows the distillation process actually worked.
Yeah, and there's more. They used TSNE analysis to visualize the internal representations the agent learned. What they found was that the representations formed these distinct clusters based on semantic meaning.
Like what kind of clusters?
Things like large objects directly ahead, or potential obstacles on the right, or clear, open, drivable area. Importantly, these clusters grouped situations based on their meaning for the driving task, regardless of superficial details.
So it didn't matter if the obstacle on the right was a red car or a blue truck. It was clustered as obstacle on the right.
Exactly. It learned generalized, task-relevant perception, ignoring irrelevant stuff like color. That's crucial for robust performance in the real world.
Okay, so let's wrap this up. What's the big takeaway for you listening to this?
I think the main point is that DGC really demonstrates a successful way to leverage the incredible common sense knowledge locked inside large VLMs for complex robotic tasks like driving. It solves, or at least significantly alleviates, those two core VRL problems: the crippling sample inefficiency and the lack of semantic understanding, that semantic gap.
And the key seems to be that decoupling strategy. Using the VLM for perception training, but letting the RL agent handle the fine-grained action control. You get the best of both worlds.
Yeah, that separation seems really promising. It suggests we don't need one giant model trying to do everything poorly. We can have specialized components working together more effectively.
So looking forward, the source material hints at exploring the balance between different kinds of representations, right?
Exactly. They mentioned digging deeper into the relationship between discriminative representations, ones that are really good at telling subtle differences apart for the specific task, and generalizable representations, the kind DGC focuses on, which ignore irrelevant details.
Which leaves us with a really interesting question to ponder. How much generalization is actually good? When does ignoring details, like the specific type of obstacle, become risky? Where's the sweet spot between seeing the general situation and needing those very specific details for safe, reliable driving?
That's the ongoing challenge, finding that perfect balance. Definitely something to keep an eye on in future